Okay, I'm recording. Okay, so we'll start where we stopped last time, which was multiplication gates for GMW. Okay, let's go to the our whiteboard. Okay, so we go back to the BGW MPC and arithmetic circuit computation. Okay. Okay. So we had used Shamir secret sharing. Let's have a notation where I would say that SI, the set of SIs, is a T secret sharing using function f of secret S. Let's see if this notation, I believe it will work for us. So this will stand for the fact that f is a T degree polynomial over some field. We will not note the field. Everything will be in the field now. T is a T degree polynomial such that S, the shared secret, is value of the polynomial at 0, and for every I 1 to n, because there's n players, okay, so n is the number of players. The share Si of an ith player is f of I. Okay, so that was Shamir's secret sharing. And BGW uses the following observation. So first of all, add gates are free, meaning you don't, the computation of add gates, if you have sharing like this, polynomial secret sharing of Shamir, then, and all the inputs are secret shared using this sharing, then you can perform addition on the inputs by adding your shares. And that's because basically this Shamir secret sharing is additively homomorphic. So just, you know, as we were talking about group homomorphisms in the context of zero knowledge, where some useful stuff that you want to prove in zero knowledge, for example, that your secret key corresponding to a public key, to a given public key, and you use the fact that the secret key to public key mapping is a group homomorphism, so that operations on the ciphertexts correspond to operations on the plain texts, or operations on the one-way function images, which are public keys, corresponds to one-way function pre-images, which are secret keys, and that's where we got efficient zero-knowledge proofs, right, for these statements. So this is another homomorphism in action, right, where shares are, you can think of the result of, you know, okay, well, some form of, well, okay, it's funny to think of this as a one-way function, but okay, it is a transformation from secrets, which are values that you share, to shares, and this transformation is additively homomorphic. In what sense? Well, that in precisely the shares that shares of one share and shares of another share can be added to form shares, let's say, like this, where this addition is simply corresponding to local component-wise addition, meaning every party computes its share of H as just adding the shares of these, right? And this is okay. All the arithmetic goes over a field, and okay, and so if this is T secret sharing using some function f of a secret s, and this is T Shamir secret sharing of degree T using some function g, I guess, of secret T, then the result is a Shamir secret sharing of a function which is a sum of these two functions over a field of a secret which is a sum of these two, right? And notation like addition of a function, right, stands for a unique function h, such that for every x, hx is f of x plus g of x, right? So we denote additions of functions or operations on the functions as a shortcut for just saying that the value of this function is the sum of the values everywhere of these two, right? And likewise, we can do arithmetic operations on functions in general. Like, so there will be a function which gives always, whatever arithmetic formula I have here on every argument. That arithmetic formula on the values of these functions on those arguments would define the function corresponding to the arithmetic formula. Okay. All right. So that's where we were last time. And now, of course, okay, what about mult gates? But we will, this fact that some gates are free, meaning, so what does it mean in context of a multi-party computation? It just means that they can locally compute, quote unquote, this gate, right? They don't need to communicate. Everybody just locally computes the shares of the output of the addition gates, given the shares of the inputs of the two wires on the addition gate. Many circuits, it would the similar question can be asked for Boolean circuits. Is there some gates that commonly occur and are somehow simple but meaningful, and you can do them for free, like in either GMW, the OT-based computation, or in YAO when you do circuit garbling? And when you take a Boolean circuit, like a random Boolean circuit, sort of a significant fraction of gates tend to be XORs. And indeed, it's possible to, so this is like the first thing that people observed. So like, in fact, you can both do a GMW and YAO circuit gambling twisted so that XOR gates are free. That's a kind of neat thing that is worth checking on. And this sort of stuff of like making twisting this computation so that to make more and more complex gates easy to go through, easier to go through is an ongoing thing. All right, what about mult gates? So okay, so what could we do? So notice if we have the same sharing as above, can I do like a mult and create a secret sharing of a multiplication? So what if they did, they just locally multiplied their shares over the field? Well, so at least, what is HI? It is a value of, if SI is, these are, right, this is, well, So what Si is what? It's share of function f. So it's f of I, and Ti is the mode, and Ti is a function g of I. Okay. So if you define, so this is actually h of I if h is a product of these two functions. The product is defined in the same way, meaning h of x is f of x times g of x for all x. Okay. So clearly, if everybody just multiply the shares of f, their evaluations of f and g, they do get evaluations of this product function. And what is this product function? Well, this is h is a 2t degree polynomial, right? Because if this is 2t degree and this is t degree, then the product is 2t degree. So that kind of works, but it works in the sense that it gives us this function, which is a 2t degree secret sharing of some function. Oh, okay. So I called, okay. So h was the value and the function at the same time. So let's change this to make the value equal u. Okay. And to keep separating, so I have the value is s, the function is f. The value is t, the function is g. The value is u, the function is h. Okay, so I call this h. Okay, so I have this function h, which is the product. So this is this function now of the u I wanted, and the u I wanted now is s times t, right? Because okay, is that true? Okay, so h is defined in this way, right? So u, which is the function that, which is the value that is secret show, h is defined as the product of these two polynomials. What is the u is defined as h of 0. What is h of 0? Which is f of 0 times g of 0, which is s times t. Okay, now is h uniquely defined? Meaning, well, every player computed some share of h. It is a correct share of h. But how many shares do you need? Well, only if the number of players is at least 2t plus 1. Because if h is a 2t degree polynomial, then we just don't have, if n is the number of players is smaller, then we don't have enough shares to, well, you know what? Is it uniquely defined? Let me think. Okay, well, sorry, it is uniquely defined, even if the number of players. So this was a wrong question. Okay, because if n is just t plus 1, then f is uniquely defined by t plus 1 shares, and g is uniquely defined by t plus 1 shares. Therefore, if these people got together and reconstructed f and reconstructed g, then they could publicly reconstruct what's this product h, right? So h is defined, even if you have just t plus 1 players. So what do I need 2 plus 1 players for? What I need them for is that if n is at least 2p plus 1, then U, which is the value shared by H. Oh, yeah, sorry. Oh, this is, sorry, I have. I forgot to log out of my mail, and my mail is connected to my phone, and every spam phone call now goes and interrupts everything I do. Okay. Then, okay, so if I have enough of these players, then the zero value of the polynomial is, it can be interpolated using some interpolation coefficient, Lagrange interpolation, times h of I, where I goes over, 2t plus 1 subset of the players. That there exists some vector of let's call this subset, let's call it the subset G of good players who contribute the shares. Okay. So the function H would be defined even if n was t plus 1, because f and g are uniquely defined and therefore H's. The point of having 2t plus 1 players is that then the H of 0 is a linear combination of the shares. So at least that part of the, in other words, then H of i's are, are simply Shamir secret sharing. Okay, they are Shamir secret. Okay, they're not exactly Shamir secret sharing. They are, H of i's are values of the 2-degree polynomial. In that sense, they are like Shamir secret sharing. They're different because Shamir secret sharing says to share a value, pick a random 2-degree polynomial and make HI's equal to the values of that polynomial at points I. H is not a random 2-degree polynomial. Is a special 2-degree polynomial who happens to factorize into 2 t-degree polynomials. Okay, so in that sense, it is not like real instance of Shamir, but at least this is true. You can still interpolate it. Okay, so it's like so these HIs are like Shamir secret sharing, but well, first of all, 2 t-degree, and secondly, the H is not a random 2t degree polynomial. Okay. All right. So, well, this is the more pressing problem. Because if you just, so, you can compute in BGW, if you just had n 2t plus 1, and you had one mult gate, then they could just multiply it locally, and at least then they could reconstruct it. Well, they would still have this problem, that it's not a random polynomial. that is a problem, because if you reconstruct this polynomial, you are giving more. If it was a random polynomial who shares this product s times t at 0, then it will be okay to publish its shares and reconstruct, because the only thing you learn from that is its value at 0. But it is a non-random polynomial who has some information in it about these polynomials. In particular, factorization of polynomial you can do efficiently. And so from the shares of H, one could factorize them and get the polynomials f and g. And therefore compute f of 0 and then g of 0, and therefore actually compute these inputs to the gate, s and t. So this would break secrecy even for that single gate computation. But that is an easy problem to fix. We will share a random 2-degree polynomial whose value at 0 is 0. And by homomorphism of secret sharing, the addition of this non-random 2-degree polynomial with a random one will give us a random polynomial. Let's do that first. Okay, okay. And why is this a problem? Well, this is a clearly right. So maybe we can compute one multigate, but we do it again, and this degree goes to 40, and we do it one more time, and it goes to 8t, right? So it's clear that we won't have enough players soon, right? We need some degree reduction step. So we need 2 steps, basically. First of all, randomize secret sharing. What do we need here? Need randomizing, some tool to allow us to randomize Shamir secret sharing. Okay, so that from a non-random polynomial that shares a value that we are interested in, we create a random polynomial that shares the same value. And here we need a degree reduction tool. Okay, let's do this one first. It's simple. Okay. Okay. So randomizing Shamir secret sharing. So if HIs are values of basically arbitrary degree, let's call it, because I want to do it for a 2t degree, I want to do it to a t degree. So, well, let's say t hat degree polynomial h at points I, and because the degree is smaller than the number of players, such that hi of 0 is my secret. Okay, and so these are my inputs. Every player shares such a thing, and what I want is random secret sharing are values of a random t degree poly R such that R of 0 is the same secret as H. You know what? Let's make a secret S. Okay. So I want a random sharing of the same secret. Okay, because then once I get this, then I can reconstruct in a standard way. I can just publish values of Ri because these are all random, except that they share the secret, the same secret as this one. So how about this? Each PI picks picks a random p hat degree polynomial called delta I, such that delta I at 0 is a 0, okay, in the field. And since a share, I will call it S, okay, S I used for the secret. So how about, you know what, let me call this like this. So, okay, so the polynomial that the PI picks is the delta with the I in the superscript. Since share delta I at jth share of this is defined as delta I evaluated at point j to pj, and it does this for all pjs. Okay, so pi has this t hat degree polynomial, and secret shares it exactly the way. So it is exactly Shamir secret sharing, but at secret equal to 0. Okay, so like it's kind of stupid for as a secret sharing, because you know that what the people are supposed to share, quote unquote, is a 0. But it will not be stupid for this goal that we are trying to achieve. Okay, because and then each PJ computes his share of this output polynomial as his share of the input plus the sum of all these shares that he received. Okay, and now let's check what this created. Okay, so RH, Rj is Hj, so it is H of j, right? So Hi was this polynomial H. Okay, so it's H of j plus, and what is the stuff? So this goes over all I. Well, so it goes over all I. And what is delta I of j? It is the delta I polynomial evaluated at point j. So this is equal to R of j if I define function R as a function h plus the sum of these deltas. Okay, so since each of them are t hat degree polys, the result is a t hat degree polynomial, right? So these local evaluations performed on shares of H and shares of all the we can call them update polynomials delta i's creates an evaluation of this function, right? Because what we are using here is use the additive homomorphism of Shamir secret sharing that we have already seen, right? We use them. We use exactly this for the add gates. All right. So now, even if so, okay. So it is a sharing of a polynomial, of a t-degree polynomial. So if you define this function, so therefore, in particular, R defined as what does this function share? It is some form of sharing, which they compute in this way, right? If they locally compute their shares, they create some form of sharing, of polynomial sharing. It's a t-hat degree polynomial values. So what's the 0 point of that polynomial? What would happen if they reconstructed it? Okay, it would be h of 0 plus the sum of these delta values, the polynomials at 0. But these are all equal to 0, right? Because that's how everybody picks their polynomials. So this is h of 0, which is the secret S. Okay, good. So this randomization did create sharing of the same secret. The final question, is it a random t-degree polynomial? And so first of all, it reconstructs the correct thing. And secondly, R is a random t-hat degree poly, independent of the input polynomial h, except it shares the same value, right? And the reason this is random because of the, it's a summation, right? So these are random t-degree polynomials. So all the coefficients, right, coefficient-wise, if you just think of polynomial addition as addition of vectors of coefficients, then along every other coefficient is the one-time pad, except at the free coefficient, where all of these are zeros. And so, of course, the free coefficient of this guy is preserved, which is this equation. All the other coefficients is a one-time pad. And it doesn't matter that some of the people who created these updated polynomials are adversaries. In fact, if there is just one good guy here, all these other contributions can be public. And as long as there is a single contribution here, which is random, that completely will randomize this polynomial R. Okay. So okay. So this is the randomization trick. And okay, and now what this randomization is used all over the place in MPCs. There is a beautiful and very surprising result called share conversion. From the authors, I remember Yuval Ishai, but there's others on that paper, which shows that this protocol is interactive, right? Each player, and actually consumes quite a bit of bandwidth. Each player shares the stuff. So it's n square bandwidth here. Everybody sends something to everybody else. And moreover, in a real system, we would need some assurance that this step is performed correctly, right? Because a single player could completely mess up this value if they contributed delta that is just random stuff. Then everybody would completely randomize their shares, and so the information would be lost. Okay. Or the bad guy could like steer them into computing, not just losing the value, but actually computing, incorrect value as a result, right? The share conversion stuff shows how to do this picking of the random zero sharing polynomials in a non-interactive way. So you pre-compute certain keys that allow you to generate random sharings of zero sharing polynomial, and and you don't need to interact. So basically everybody magically gets the share. Okay, it's like the keys that they pre-shared allow them to generate locally these shares of a quote-unquote random, or random enough. So it will be random, but in a computational sense only, right? So whereas this is perfect information theoretic, with these keys, you would get values which are pseudo-random. Okay, so quite surprising, right? Like when you see this, that this would be possible to actually get rid of all this interaction in such application. Okay, so let's go to the degree reduction. So we have so they locally multiply, and then they do this randomization step. So now the question is degree reduction. So the inputs are well, let me just use okay, fine, let's start with so I will continue using the same notation. HIs are values of 2t degree polynomial h, such that oh my goodness, there was a typo here. H of I is not a secret. H, the polynomial h evaluated at 0 gives you a secret. Okay, so HIs are values of this polynomial. Okay, so hopefully, I don't know if you noticed this typo and just overlooked it. Okay, that's what it's supposed to be. Such that H of 0 is a secret S. And what we want is values, let's say Zi, so such that there are values of t degree polynomial Z, such that Z of 0 is the same value S. And we will not worry about the Zi being random because we can randomize it using this trick. We'll see if it was important for H to be random at all. Perhaps it won't be. Okay, but we'll still use randomization at this step. Okay. So let's go back to this to this fact. Okay. So note, for simplicity of notation, assume n is just 2t plus 1. So this way we don't have to talk about picking some 2t plus 1 subset. Instead, we just say all players. But that's just for simplicity of notation. So so under this assumption, the secret S, which is H0, is a sum of simply all for over all players, all n players, of Li times H of I for this set are where this set is Lagrange interpolation coefficients, right, which are the sets from last lecture. I wrote on the notes. There is a formula for how you compute them. I'm just thinking in my head, do I remember the formula to do it? I don't want to mess this up. Once you have all players in the so the formula is, it's a product, and you subtract the value at the argument from at which point you want to compute, which is a 0, minus, so it goes now over all j not I. So because we take the all players, so there's no longer a subset that we need to consider, which is simply all. So it's all except of the I point. So this is a minus j here in the denominator, and in the denominator we have I minus j. So in general, this is the interpolation. So using the values of the function at point I, you can compute the function at any argument if you use this argument here. So it's the argument minus the jth index over the value at which this is evaluated minus j, right? So it's the product of these of values like this, but it simplifies here, because the argument we want to interpolate is 0, okay, and the values at which we have evaluations are the i's, okay. So these are these alpha i's, and they are public, right? Because everybody knows the indices. That goes from 1 to n. Everybody can compute. Okay, all you need, because it's a field, for these to be different. By the way, this does restrict you to this choice of field. The field has to be at least as big as n, because you have to have n indices in the field to assign to every player an index. Otherwise, there will be zeros here, right? So in a big arithmetic circuit, this is not a problem, but like if you wanted to do this over small fields, then it's a question. It's not clear how you do this. Okay. You would do it in an extension field and then take the result down to the right. So if you want to do it in a binary, you have to work with the field extension field to do the whatever that is larger than the number of players. Okay. So we have this public linear formula, and visually there is values h1, h2, all the way to hn. And now what we are going to do, and this is the secret S. Okay, so the line is the polynomial h. And these are just evaluations of the polynomial h. This is h of 0, this is h of 1, this is h of 2, dot h of n. So in this degree reduction step, what I'm going to do is that I'm going to create, each player is going to create his own secret sharing polynomial. Let's call it delta 1. And this player will create a polynomial. So h, this is the line for polynomial h. Degree of h is 2t. The degree of all these polynomials will be t. And this guy too, his degree is going to be t. And so just as in the degree, in the randomization step, where they were sharing some non-random t-hat degree polynomial, and they outputted a t-degree polynomial that was random and shared the same value. How? By generating random t-hat degree polynomials and using additive homomorphism of the polynomial secret sharing. Degree reduction will actually work very similar. Every player will secret share using Shamir secret sharing a polynomial delta I for player I. But now these polynomials in the degree reduction step, what they share is not 0. This polynomial will share h1, and this polynomial will share h2. So what does the player hi do? He creates a polynomial h of I, and so of course everybody degree is t. Okay, and the last player generates delta n, the degree is t. Idea, each PI shares using the polynomial or actually in terms of secret sharing, what they're sharing is their own evaluation point. So they're sharing their share. HI is the share of S, which PI possesses. What he will do with this share is that he will secret share it by creating, using a T degree polynomial delta I. Okay. So what's the protocol? Each PI picks a random T degree polynomial delta I, subject to the constraint that delta I at 0 is the share of that held by that player. Okay, and does what with it? And sends a value of this polynomial at point j. So let's call that value somehow. Let's call it S. Okay, sorry, it's saying S the secret. Si j, which is a value of the polynomial si evaluated at point j to player pj, and that is done for all j. Okay, so in other words, PI simply performs a standard Shamir secret sharing. So this is exactly Shamir secret sharing of HI. Okay, nothing new here. Now let's see what values player PJ gets. So from the first play, so he gets the value of the first polynomial at his point, at his index, and he gets the second polynomial at his index, and so on. So for every polynomial, he gets a value at his index. And let's define polynomial sigma or delta, I guess, as the sum of delta i's for all I. Note that shares every pj holds a share of each of these component polynomials. Okay, so this is the case. It is additive gate. They are computing an additive gate here. They held, their inputs are the shares. They secret shared those inputs. And now they need to add them. It's an addition gate, except it's needed to addate with these coefficients, right? The secret is not simply a summation of HI, it's a summation of HI with an added factor, but the factor is public. Everybody knows these factors. So it's an additive guide with public factors alpha, lambda. They are not a problem because everybody can simply multiply their share by a corresponding lambda. So observe if the set of SJIs, the set goes for J, is a T-degree secret sharing of HI using what polynomial? Using polynomial delta I. Then, if you locally multiply your share by this public factor alpha I, then you are gonna get a T-degree secret sharing using a polynomial that basically is this public factor times the polynomial, right? So I can multiply a polynomial by a constant. Every coefficient is multiplied by this constant. At every value, the value of this is the value of that times this constant. Of, you know what? I don't care what polynomial this is. It is a T-degree secret sharing of a value which is alpha I times HI, right? This is simply, if you have a polynomial that that evaluates, if you take a polynomial and multiply it by a constant, then every local value of this polynomial is multiplied by the constant, and the value at 0 is multiplied by that constant. Okay, it's as simple as that. So now, therefore, these public factors are not important, because given the share of delta I, everybody can locally compute the share of, sharing of HI, everybody can locally translate these shares into the sharing of HI times a public factor, lambda I. And now use the additive homomorphism of Shamir secret sharing to locally compute the sharing of this summation polynomial delta okay. Basically, locally compute degree secret sharing of the sum of alpha I HI, which is equal to the secret. What was this? Alpha I HI S. Okay. So in other words, at this point, the players hold secret sharings of lambda 1 H1, lambda 2 H2, etc. Right? So the lambda I HI values are all secret shared. Since this secret is just a summation of these lambda I HI values, we use additive homomorphism to locally compute, simply add all these shares, and this will give us a sharing of the target polynomial. Okay, and what do we know of this polynomial? Well, it is what's the degree of this polynomial? Each of these is t degree. So added together, this is a t degree polynomial, right? So that part checks out. The value that is shared by this polynomial is the summation of these values, which by this formula is the secret that we need. And is it a random polynomial? Actually, it is. So we don't even have to randomize it, because as long as at least one party here is honest and not an attacker, and therefore at least one of these polynomials, delta, is fully random, subject to the constraint that it shares the correct value, because in this addition step, it suffices for one of them to be the random, subject to the constraint that they share the correct value, for this result to be random, subject to the constraint that it shares the correct value. Okay, are you good? Sorry. Oh my goodness.
I think your microphone is broken.
Something. What I got is something absolutely horrid. Just a Yeah, sounds okay. So it's Bruno's mic is broken. All right. Bruno, if you want to communicate, send a text. All right. Yeah, sorry about that.
Oh, how about now?
Oh, now it's better.
Oh, come on. Like Zoom keeps like changing my microphone to the USB camera one, which is terrible. So sorry about that.
Yeah, it's okay. But what did you want to say?
No, I think it's fine. It's just essentially you are resharing the shares, right? In a
Yes.
way that you only need T. So
Yes.
I think it's okay.
Yes. So all, this is just a generalization of additive properties of Shamir secret sharing. If the value is some additive formula of the inputs, then we can, it doesn't matter that these were 2-degree values of a 2-degree polynomial. As long as there are just some values and we want to compute an addition of them with public factors, but the public factors don't matter by this argument, then we just use the same trick as in randomization, right? Everybody shares and you add these secret sharings. Okay. So in a sense, the mult gate reduces to an add gate. Okay, you locally multiply your shares of the input wires on the mult gate. This defines an addition equation by the interpolation formula, and then you perform an addition gate on those. But you have to. It is non-interact. It's not non-interactive. In other words, you need interaction because, okay, so each of these players hold locally this additive component of the secret that they would like to ultimately share. But now each of these players needs to secret share this additive component. So that's where you need all this communication, right? And so it is. It uses n square communication. And what I said about the zero sharing, that it can be made non-interactive, it would be very nice to reduce the bandwidth complexity of this. Okay, is there some way that we can pre-share something to save on the communication here? And the answer is yes, you can. Okay, so not obvious how. Let me think. Actually, hold on. So the pre-sharing trick, is it really safe asymptotically, or was it? So far we didn't get to how to do this for when players are malicious, because just like in the randomization step, a single player, if he just sends complete nonsense here, right? For instead of sharing a t-degree polynomial that secret shares the product of his shares, right? Of the two gates, he just sends random stuff. It's not even a t-degree polynomial. Okay. Well, then he completely messes them up because they locally add. So this polynomial is going to be not a polynomial at all. It's going to be, n random values, right? So it will obliterate the computation from then on. That's one question. And another is like, well, apart from obliterating, could you steer the computation in a bad way? Or could you steer the computation in such a way so that it will reveal more information about other players' inputs? These are questions. One answer to this is to replace what is the tool that we used all over the place. It was basically Shamir secret sharing. Here it was Shamir secret sharing in the plain form. Okay, you just exactly perform Shamir secret sharing as a black box on these inputs, and all you use is its additive homomorphic properties. Here was almost Shamir secret sharing, right? Like, so it was a Shamir secret sharing of 0. So in fact it was, okay, just share a secret equal to 0. Kind of an absurd step in terms of secret sharing, but yet possible. And then you can use black box properties of Shamir secret sharing from then on. So if we replaced then each of these steps, secret sharing with something called verifiable secret sharing, then we would not plug all issues, but many of them. Okay, so let's. So here's what upgrade. Okay, so I guess let me reiterate. We're done with BGW, right? We're done with BGW because we can use secret share using Shamir, add gates, non-interactive, merge gates, you know now how. And so now you reiterate over the circuit, you perform each add gate this way, each merge gate this way, you go from shares of inputs to shares of outputs. Finally, you have shares of all the output wires, you reconstruct them. Okay, so that's BGW. Now, the upgrade from honest but curious folks who occupy T of these players and follow the protocol, but only what you're concerned with are the shares that these players get. Do they let them know anything about the any additional information about the circuit, about values on the circuit, inputs, intermediary values, than what's visible from inputs and outputs? And because these are black box sharings, it's just properties of the sharing, so to say that no, they don't get anything. All they get for every wire is their shares of secrets on that wire. And by the properties of secret sharing, that is information theoretic independent of the value on the wire. Okay, but what about if they are not just honest but curious, but active or arbitrarily malicious faults? Okay, so in other words, the T bad players can divert from prescribed protocol. And the basic tool would be replace secret sharing by verifiable secret sharing. Okay, what's verifiable secret sharing? The sharing procedure given X creates these shares, right? And the reconstruction procedure given some large enough subset reconstruct the secret for any subset large enough. So let's say we want perfect. I mean, if there's T bad guys, clearly any T players cannot reconstruct, but T+1 can. Okay. You can also have a gap between how many you allow bad guys to and how many good guys are needed to reconstruct. But let's try to hit this. And so the standard properties of secret sharing was that any T shares of these don't give information, and that's it. The verifiability means two additional properties. First of all, in sharing, if honest, if any honest party outputs party PI outputs during the sharing phase a share that is not a rejection symbol, then shares SI of honest players will reconstruct to some unique secret X. And this, as long as the number of honest players is at least T+1. Okay, let's try to, we can do it relaxed. Maybe we need to require actually for some techniques more honest players than T+1, but that would be the best setting. Okay, if the number of faults and the number of faulty players is at most T. Okay, and therefore N has to be at most 2T+1. So in verifiability in sharing means that if there is a dealer and he communicates with these players, if this guy is honest, then after the sharing phase ends, he needs to be convinced that whatever this guy shared, it's some unique value. So that it's defined at that point. So that subsequent malicious activity of, that basically, you see, in this step, for example, the very minimum of honest players here who are receiving these delta-1 shares is this is P1 share anything at all? Is this what we're getting? Are we getting values of a T-degree polynomial? Or are we getting some random garbage that doesn't even interpolate? It's not a T-degree polynomial. So therefore, if we use this and add this, we are going to make the results of the circuit completely obliterated from now on. Okay. So it's like the minimum that they want to know. Is this values of some T-degree polynomial? In addition, we would also like to know that the secret sharing shares not an arbitrary value, but a value with some properties. Namely, it's a product of the shares of some previous sharing that this guy got. So that's a separate thing. Okay, but the minimum is this form of verifiability. And then in reconstruction, if SI shares formed form a secret sharing, then presence of up to T malicious parties at reconstruction cannot stop from reconstruction formed as sharing of some value of X. So when these parties now decide to reconstruct, they will successfully reconstruct this shared value, even if T of these guys try to contribute wrong shares. Okay. And I'm out of time. So you know what? Let me just quickly do one. Okay, because this is just a terrible place to end. So here is here's one secret sharing. Okay. So recall Pedersen commitments. The commitment to a value X is G to the X, H to the R for random R. R is the commitment. And GH are random group elements in a common reference string. So nobody is supposed to know the discrete log or between them, or the commitment will not be. So the commitment is information theoretic secret. So a value like this does not reveal any information about X, but it's binding subject to hardness of computing a discrete logarithm between G and H. If somebody is able to commit and then decommit in two ways, then you can actually compute the discrete logarithm between G and H, and vice versa. If you know how to compute the discrete logarithm of G and H, then you can cheat in binding. So G and H should be pre-agreed. So this is a Pedersen VSS in the CRS model. And let me think offline whether you can upgrade it to an arbitrary, so they basically everybody would have to pre-agree on this G and H. So let's leave this aside. You can say, well, okay, how about a coin toss, a distributed coin toss? But remember one coin toss I showed you between two parties. So can they come up with G and H random in a coin toss? But the coin toss I showed you was everybody commits to a random value and then decommits. And the value agreed on a coin toss is, let's say, XOR of all the contributions. Well, I needed commitment as the tool, and now I'm, it's a chicken and egg, right? Okay. But let's say in random oracle model, a commitment could be a hash, right? So you could just take a SHA and do this coin toss to agree on this GNH. Okay, so that's a Pedersen commitment, and now I can use it for Pedersen VSS like this. Dealer picks T degree random T degree poly F. So dealer at who wants to secret share X F is subject to the constraint that f of 0 is X. This is like Shamir secret sharing, right? So far, but also picks let's call it a shadow polynomial, which is a random G degree polynomial f prime, and not subject to any constraints. Okay, it's just a random. It's a T degree polynomial, but it's completely random. Dealer sends the following share to each player: SI TI, which is f evaluated at I and f prime evaluated at I, to player PI, and he does it for all players PI. So, like Shamir, but both on F and on this shadow polynomial F prime. But in addition, dealer broadcasts, and here we need a reliable broadcast. I'll explain in a second what that means. A broadcast the following set of values. The values I will call the CI. Each of these CIs, let's call them CJs. Okay. It's okay. Let f of x be a0 plus a1x plus at xt, and let f prime of x be b0 plus b1x plus bt x to the t. These commitments will be a commitment of Pedersen commitment to coefficient j, aj, using the coefficient of the shadow polynomial f prime as the randomness. And he publishes for all coefficients. Okay, this is one big commitment, okay, which is a vector of these commitments. He broadcasts this. A reliable broadcast means that if is the property, if some honest PI gets this C on this channel, then all honest players receive it on this channel. In other words, if this this C, this vector of Pedersen commitments to coefficients of the secret sharing polynomial combined in this way, will form a commitment to a polynomial. And the verifiability will only work if everybody gets the same commitment. if you and I get different commitments, then we can locally verify that the commitments look fine and that we got the commit values that were committed here. But if you and I get different commitments, then this is a useless verification. This commitment has to be, we have to be assured that it's the same. This basically passes the buck. How do we get reliable broadcast in a network? In some networks, I guess you can assume that there is a public broadcast, and if something is sent on the wireless, everybody in the local area network gets the same value. It's probably not even true then necessarily, right? But okay, under some assumptions on the hardware, it will be. But these assumptions might be iffy. Clearly, over the internet, it's not clear how broadcasts like this would be implemented. So this is another story, a beautiful story in distributed algorithms for how to implement this in a distributed network, okay, where there is no natural broadcast channel. You only have point-to-point links, okay? But let's, okay, but these protocols exist. It's possible to implement them. So it's using CRS and reliable broadcast. Okay. Okay. And what does what was this? Each PI verifies that his local share that he gets, if he performs this one-way homomorphism by taking the exponents SITI and computing them jointly in this way, then what is this? This is G to the F of I. But F of I is a summation over the coefficients, AIs, with some, I to first, I to second, I to third. Every I is a public value, so these are just factors in front of the AIs. So this is, I can take a product of these CJs from J0 to T and exponentiate them to I to the J, right? Because why is that? Because both of these should give me, this is the product over what's CJ, it's G to I to the J times AJ. And this is a I to the J times BJ. So that's the same as G to the sum of alpha IJ AJ. And this is the H to the sum IJ BJ. So this sum is F of I. And this sum is F prime of I. So that's what it's supposed to be. Okay. So what we are using is the homomorphic property of this commitment. Given Pedersen commitments to coefficients to this, let's forget that B is supposed to be a polynomial. Let's just think of this as a randomness in Pedersen commitment. So these are commitments to AJs. And your value that you got, which is SI, can be expressed as a sum of the AJs modified by some public factors. These public factors are I to the J. So it's like a weighted sum, right? So just like in case of the degree reduction step, these things were shares of sum HIs, and we didn't just want to compute a product gate. It's a summation gate. It's a summation of gates on the inputs that are moved by some public factors, where the role of these public factors here is played by this I to the j coefficients in front. Okay, but otherwise it's just a multiplication. It's just a product. Sorry, it's a summation. Yes, it's SI can be expressed as a summation of AIs with these I to the j factors in front. And by additive homomorphism of Pedersen commitment, given the Pedersen commitment to the AJs, you can compute a Pedersen commitment to the sum of the AJs, which is your shell. Okay, and okay, so sum to the AJs, it's AJs with this shifted by these coefficients, but otherwise it's just a sum. So it's a weighted sum. Okay, so that's what you use here. If verification fails, PI broadcasts a protest, meaning PI just broadcasts that I'm being cheated. I didn't get the proper share, and because it's a reliable broadcast channels, every honest player is going to get that message. At this point, right? So, okay, let's say that for every honest player this verifies. C is a commitment to a t-degree polynomial because it's a commitment to t+1 coefficients, and t+1 coefficients define a t-degree polynomial. And if you know the argument for why this is a binding binding under discrete log, computationally binding, extends, right? I mean, it's just a black box argument. Like if it was if the binding property works on each coefficient individually, then the same property works on this whole vector as a commitment to a polynomial. And by this additive homomorphism of this commitment to coefficients implies commitment to evaluations of this polynomial, which are shares. So now, why doesn't he simply send a Pedersen commitment to the shares themselves, and now everybody locally just simply computes that his share corresponds to the commitment to the shares? Well, because if I send you a commitment to the n shares, it wouldn't be clear that this is a t-degree polynomial inside. But if I send you a commitment to t+1 values, then, well, it has to be a t-degree polynomial that is effectively committed in here. Okay. Did this leak any additional value, this broadcast? No. Although there's not quite a black box argument, because, well, it didn't leak on polynomial f, right? Because at this point, basically BJs, which is some t+1 values, can really be treated as a perfect randomness, right? They were chosen at random, because if you choose this f prime at random, that exactly means choosing each of these things at random. So if that's all you get, then this is an instance of just black box usage of Pedersen commitment. But you also reveal something extra about this randomness, namely this thing. So it takes some convincing that, okay, that these two leakages don't combine badly. But you can, it's not so hard to see that in spite of this sort of side information, if you think of T bet players, they get T shares. The only secret is this, A0 and B0, right? Because if you get T values, you're not getting these coefficients exactly, but you're getting T equations. And so there's the only degree of freedom is a single degree, okay? But still, these are both of them, after seeing T values like this, both of them are perfectly secret. Now, seeing additional T+1 equations like this, basically T of these equations give you nothing that you already didn't know. But there is one more equation. It is an equation that binds A0 and B0 into Cj. Well, that of course gives out information about A0 and B0 jointly, but B0, you're not really interested in it. The question is, did it give you information about A0? Because that's the real secret here. And that's the black box argument in perfect secrecy of Pedersen commitment. It doesn't, okay, because B0 is random. Okay, so this is a little bit hand wavy, but it is why this commitment, giving these broadcasts does not reveal any additional information about the secret. All right, so still, if all the honest players this verification passes, then we would be done. But what if the malicious dealer, sends these commitments badly, right? So at least one player is cheated, or the commitments are fine, because indeed every set of commitment is a commitment to some T-degree polynomial, but simply to one player he gave a bad, say player 1 gets S1 T1, which is not equal to whatever polynomial is committed in this vector of Cj's. Well, in which case P1 would have to be able to protest, or this property would not be assured, right? Because all the good guys got their share, but P1 didn't. So the reconstruction afterwards would not be guaranteed. In fact, it would be impossible. All the bad guys shut up. They don't say. P1 got irrelevant stuff, so there is a missing share. You cannot reconstruct. But if this guy protests, then the dealer must follow up with broadcast of SITI that verifies this equation. So if somebody feels cheated, then the dealer simply publishes their share. Why is that okay? Two cases. So if this guy is bad and he just wants to make some share public by pretending that it was badly delivered, well, so he causes this share to be public. But if the dealer was honest, and that's the only case in which revealing the stuff that the dealer produces is relevant at all, because if it's a bad guy, then well, whatever, the adversary already knows what he knows. Well, but PI already got that share in that scenario, right? Because if the dealer is good, then PI already knew it. So the only thing that the bad PI can cause using this protest is publication of his own share. So this didn't really increase the amount of knowledge which attacker has. And now, did it stop all forms of cheating from PI? Yes, because after all these protests are follow-up, so first of all, must follow up that verifies, so all honest player, all players verifies it. So now from point of view of honest, if there is T+1 honest players in the system, then if they were not cheated to begin with, then it means that they did have shares that correspond to this unique polynomial that is unique up to the binding property of Pedersen, right? But if you cannot break the bindings, that is a unique set of HJs and therefore a unique polynomial F, and therefore a unique secret. So if good players got their shares at this point, they already hold those shares. If any of these good players didn't, then it must have been broadcast afterwards. So either way, you always get some T+1 shares that do correspond to this shared value. And therefore, once you reconstruct them, you do get the shared value. I didn't show you the reconstruction phase, but it is obvious from this. Because this commitment is public, the reconstruction is just a standard Shamir reconstruction but on both F and F prime. So everybody broadcasts their share. And everybody verifies this equation, right? Again, only good shares will pass. And if there is T+1 good players in the system who accept it, then there are T+1 good shares. So there is T+1 shares which will pass this equation, and these would be the SIs on these, right, will interpolate to this unique secret sharing polynomial that was committed in here. Bad players cannot mess this up because of by the binding of the commitment. They cannot create values that pass this verification equation, except if either they break the binding of this commitment, or their values are actually correct. They are simply evaluations of the same polynomial at their indices. This, of course, this poses also so it works. It has quite a few rounds. It uses now a reliable broadcast as a part of the MPC. So now for each gate, they have to use this. Well, where did they broadcast? Well, first of all, during sharing, right? So at the initial phase of BGW, everybody had to reassess their secret share, their inputs, and now we put VSS there instead, verifiable secret sharing. So they will use this protocol at the beginning. It's bad enough, I guess, but what's even worse is that they would have to do it for every mult gate. Did it increase asymptotically bandwidth? Not really, because it was n square to begin with, and what this is order of n for every player. Okay, but kind of it did and didn't. It was n square of point-to-point messages. Now it's n square over the reliable broadcast. The reliable broadcast itself, how is it going to be implemented? Well, actually, if you look at these protocols, what happens in reliable broadcast is that they ping-pong this message to one another to agree on what it was. That will be again, but using collision-resistant hash, I guess they can just agree on the hash of the message. Okay, so that's not gonna negatively impact. Okay, so the size, I guess it doesn't. Yeah, I guess it doesn't. Also, not 100% sure. Just when I say that. But okay. Another thing that it introduced public key cryptography. So everything in BGW was just Shamir secret sharing, so operations on the field, so just plus and mult. These are fast operations. The field can be short. It could be an extension field of 2. It could be like 2 to the 8, right? So operations on that field are in a processor, both a mult and a product will be very fast. Suddenly, now I have to exponentiate, okay, per every mult gate, because I do have to have the ZSS for every mult gate. This is as if, I started with garbled circuit, so I do symmetric operations per every gate, and now I retrograde back to a heavy public key solution, which GMW, for every gate, it performed OTs, which in the basic form required public key crypto. Okay, so that's this thing. Okay, so it's nice, but it's in no way a perfect solution. In fact, MPC protocols that are based on BGW, ones that seem to be the most efficient, it's the so-called SPIZY framework, and there are other papers like this. They use arithmetic computation over the BGW standard computation, but for VSS, they do a much faster version of this, which uses so-called check vectors, and maybe that would be worth showing next. Okay, and sorry for going over. And I'm going to send you some exercises today, because you are due for some. Do you guys have any questions?
I don't have any.
Okay. All right. Have a good weekend and see you next week.
Thank you.
Thank you.